2018 Statistics and Applications, Session 7. In this video, I'd like to discuss two very useful tools, and they are called covariance and correlation. And to start the discussion, I like to motivate it with a situation. All right. So let's just have some data points, right? Such as this, three situations. So these are XY axis, right? And we wonder if there is a tool, a sort of a sensor, to tell us that perhaps the data points here are pretty well aligned as a line. Sort of like we hope to have a sensor that can see this line and tell us, hey, I saw a line, right? That would be nice because it's one step towards AI, yeah? And even if it's not AI, the ability to tell a line is one step towards feature extraction, to be able to detect linearity and all that. And of course, we also hope that it can be powerful enough to accept some noise and then tell us, hey, you know what? This appears to be a line. I see a line, even though there's a distraction here, right? There's a bit of a noise, so it's a bit noise tolerant. And hopefully it can tell us, I not only see a line, but it's a negative gradient. And in perhaps other cases, like we have a lot of data points and it's very diffused, then the sensor will tell us, I don't see anything, right? So example, the reported value could be, oh, this is plus 35. And the sensor says this is negative 15. And the sensor says this is about -1, 0, 1, I don't know, like 0. That would be nice, right? So that would be nice. And indeed, we have that. And that's not surprising. That's called the covariance. So covariance plays this almost magical role of being able to detect linearity, the shape of a line. The shape of a line. So maybe it has some sort of a cockroach intelligence in that sense, right? It's able to tell a line. And let's talk about that a little bit more by, first of all, studying the formula, the definition. So we have this covariance, xy, and it accepts two variables, right? X and y, because it's co. Co means, we wonder what's the relationship between the two sets of measurements, two random variables, two populations, x and y. The population version is supposed to be 1 over n, the sum of all the numbers from 1 to n, each point minusing mu x. Remember mu x? Mu x is the population mean of the x population times yi minus its own population mean. Yeah. And we have also the sample version. Sample, normally we put a bar on top, right? Yeah. So x bar is a sample. So I'm just going to similarly indicate that. Maybe I put a tilde here. Because normally we use small letter values to represent samples, but just to have some symmetry here, right? So sample will be sample size n minus 1. So it does remind us strongly of the definition of variance, yeah? And that's not surprising because covariance is a kind of a generalization of variance, as we'll see in the properties of covariance in a bit. Okay, so if we define, so if I can define SS x as sum of all the numbers from 1 to n, xi minus x bar. That means the sum of squares, sum of squared deviations of x. And remember, these are for samples only, because we want a easy way to compute, not easy way, but a shorthand way to compute, to write down the formula. So in order to compute, everything must be based on samples. We cannot touch the values in the population. Untouchables, right? And one more thing, SSXY to be sum of I equals to 1 to n, xi minus x bar, yi minus y bar. So if we have these convenient notations, I mean, they don't change anything. They're just, because we keep using sum of squares, right? Sum of squared deviation of y's and sum of squared deviations of xy. So because we keep using these sample calculation values, it will be helpful if we can just define the shorthand notations for them, for samples only. Okay, so they make sense only for sample. We will never define anything that is xy minus mu x, because that's the ultimate, right? Because we're trying to study the population. That's the goal. That's there's no need to keep repeating the use of mu x, mu y. But we do have to, in this discussion, keep referring to the sum of squares a lot, quite a bit, because we have already seen this, that the sum of squares, they are nice because they total up the non-negative, the absolute values of the errors in some sense, or deviations in some sense, squared by squaring them. Once we square them, the values get enlarged, but the good thing is the negative signs become positive and they don't cancel. So errors can only be enlarged. And so if we can minimize the errors, then we will know that the data points will hug along the means, right? The mean values well, in some sense. And yeah, so that's what we're going to go along with. And so if you use these notations, then the population we cannot rewrite, but clearly the sample version, we can rewrite it as 1 over n minus 1, and this is exactly SSXY, right? So we can just directly put on top SSXY. Okay, which is far more revealing that, oh, it's just sum of squares of the xy's, the products of xi's and yi's, divided by n minus 1, which is like the denominator for variance as well, variance formula, right? So that's much more revealing. And number two is I just used n, right? Yeah, but I have two variables. And when we learned about hypothesis tests, the paired unpaired test for two populations, we didn't have to worry about n1 and n2, unless it's paired, right? And here, in this case, we have to have paired situation. There's no such thing as unpaired scatter plot like this, right? So all data points will have x values and y values at once together. The moment I plot a point, we will have that right away. So that the number of data points will always be n. So let's just put it that way. N equals to number of data points. So our X and Y, they are kind of like a simultaneous measure of the same phenomenon, same entity, same situation, right? That's why the pairing is always very strong. Example, we can always wonder, right, whether the height of a person is linearly related to the weight of a person. Because it's the person, it's the same person. There's no meaning in associating my height with your weight, right? Doesn't make any sense. But in practical situation, this is probably a trivial one because I'm just trying to give an illustration. But it is perhaps essential in some social occasions where we want to estimate the person's weight, but socially it's very rude, right, to ask how heavy are you, right, unless you know the person well as a friend, and even friends will say, hey, that's none of your business, right? But if you have enough data points, maybe amongst your friends or what, to know that there is a positive correlation between height and weight, then what that means is the taller you are, the heavier you are. We wonder if that is true. We suspect that is true, but we don't have anything to back us up, right? Until we collected this set of data points and we have evidence now, right? The taller you are, the heavier you are. Okay, so that remains a suspicion unless we have data points to support us, because we suspect there's some relationship, right? Because a person cannot be 2 meters tall and then weighing like a feather. Neither can a person be 1 meter tall only and then weighing like you know 500-pound gorilla. Okay, maybe you have a real example, but don't tell me. Right? It's very rare, right? It's very rare. And it's nearly impossible. So we wonder if it's true, and if you can have such a relationship, right? This height and weight relationship, you know it's evidential. Then you can look at a person's height and guesstimate the person's weight, whether it is heavy or not. You might laugh it off, right? How useful is that? But I would suspect airline staff might be trained to assess the person's weight. Maybe not so much in Singapore, but in some countries, passengers could be very obese, very huge, right? And airlines have been known to charge that kind of passengers for 2 seats worth or even 3 seats. So how do you initiate that extra check, not extra service, extra check? Please step aside, sir. Right, please step aside, ma'am. We would like to check your weight. Now that is already very discourteous, right? So before you initiate that, in the staff's mind, there should be some assessments, isn't it? Yeah. So they would have been trained, and during the training, what do you think the instructor will say or will provide convincing evidence to make sure the trainees, the airline staff, are committed, right, to visually check a person's weight? Oh, well, you can look at the height, right? Yeah. So the instructor is likely going to show some evidence, and this will be the evidence. You see, so that the trainees will be convinced. Yeah, okay. So height is actually a good teller, right? A good indicator. Now, even though I've mentioned this, did you realize that height, right? We use our eyes to estimate, right? Now, yeah. We only when we our eyes trigger this high weight. But how high is high, we don't know, but we know it's very high, right? Then we invite a passenger for the extra heavy weighing machine to determine whether the person should buy 2 seats or 3 seats. So when we look at the height, this information, or rather this sample, right? This population, this remember our sense of population in statistics is a set of numbers, right? So the population of heights is an easy or cheap population to sample. That's the deal, right? That's the deal. Because it is, you are always offending customers when you say every passenger please step on the weighing machine, right? So sooner or later, the airline is going to report losses for quarters after quarters because people feel very insulted, right? And you just alienating customers. So talk about customer service. That's really a disservice. However, if you can, surreptitiously without annoying most passengers, because most of them are okay, right? But only do that to very, distinct passengers and based on data analytics here, then you are able to protect the airline's profit integrity, right? But at the same time, be fair to other passengers as well, because indeed, right, if you are weighing twice, three times a person's average weight, then you are consuming twice, three times the airline fuel to take off and land, right? So you know ought to pay the fair share because otherwise other people will be subsidizing, right? So perhaps there's some reason, although it doesn't sound nice, right? But there's some reason to that. There's some justifiable reason. So the thing is, cheap to sample, expensive to sample. Did you get that? Yeah, cheap to sample, and quick and dirty, quick and fast to sample pretty accurately because our eyes cannot tell millimeters apart, centimeters apart. But right, extremely tall, extremely short, we can tell. Weight, we can't tell. We cannot see, we cannot smell, we cannot touch and know the weight. So, and then of course, the only way is, sir, please step over and stand on the weighing machine. Right, a very very costly gesture, right, to the dear customer. So I hope you see this, that we can use this kind of linearity to not just solve mathematics, but then solve social situations, business cases where one population is cheap or easy or painless, right, to obtain. But what we want to know is the hard to achieve, hard to measure, hard to sample, expensive to sample population values. This one, right, the weight. Okay, so that is if they exhibit some sort of a linearity. And even if it doesn't, approximate linearity is good enough, right? Yeah. How do we know that? Thankfully, now we have our statistical sensors, the covariance, right? So we then can make use of covariance to run the data without having our eyes to eyeball them. Although I always advocate for my students to just simply plot a scatter plot to have a look, right? Because in the past it's very expensive to plot scatter plot accurately because you are using it to study more in-depth behavior about the data, right? So it better be to scale, right? Because initially you don't have any idea what is the relationship or lack of it between X and Y. And that's why you want to plot them very truthfully, very honestly, right? And therefore, they better be to scale. You cannot just roughly dot sketch them like I did here because I'm just doing illustration. But you really spend the money and time, right, to gather the data, then you better plot them accurately to scale in order to hopefully get some insight, right, like linearity on the shape of overall points layout in that sense. So covariance is able to kind of put a crosshair in the center of gravity of the data cloud. I'm going to call this a cloud, right? Even if it's a line, this is potentially a cloud that has, before we plot it out or measure it, we have no idea what the shape is. So this crosshair is going to center on the X bar and the Y bar. All right, so they're going to center on the X bar. Now I'm going to use X bar rather than mu X, huh? And I actively make that difference because X bar is what we can definitely know is in the middle of the points we have seen. So is Y bar, all right? But not mu X, mu Y. So mu X, mu Y is like, at this point in our discussion, is like so far away from us that we are not even there already. We're not trying to determine mu X, mu Y now. Our goal is very different. Huh? Our goal now is to see if there's a shape. In particular, more specifically, the shape of a line. We start off very simply with the very humble goal of determining if there's a line. And if there's a line, we're not talking about the gradient. Huh? We're not talking about the gradient. We are saying this is more a line than this is a line. How come? Because there is a shape. There is not. There's a noise. There's more noise here, so the strength is less convinced, less convicted to say that it is a line. However, the sign does say that the line that the covariance C is more oriented in the negative direction. That means if you do calculate the gradient, you should get a negative gradient. However, the number is not a gradient. Don't get that mistake. All right. So the number here is not a gradient. So the idea now is that if you have a data cloud, then covariance will exhibit a greater than 0 value, right? If your data clouds, they are around, scattered around like this, right? So most of the points are actually forming a line. Of course, the points themselves don't know each other, right? So you just measure. It's like height and weight of every individual. They don't really synchronize with each other. But because we are all governed by DNA, right, and biology, human biology, that we end up that way. So if we are 1.5, if you're 1.6 meters, if you're 1.7 meters, you can vary in your weight. You can be plump, you can be obese even, or you can be skinny, you can be super underweight, malnutrition kind of underweight. There can be still a wide range. Doesn't mean you cannot. But most people will not be like that, right? So that's why it will be still exhibiting this, plus some noise off center. So these are dots that are intentionally drawn, which will be the outliers, right? The outliers from the main line in that sense. All right. Outliers are not like particularly large or low values of X or Y, but combined together relative to other majority lines, points that lie on the line, they are outstanding. They stand out on themselves, as you can see in this setting. Right. So the other way around, like I mentioned, we would expect that the data cloud, if they are exhibiting this fashion, and then with some noise off the diagonal, then covariance will be very negative. And if they are very, very, how do I call that? Hugging, very much hugging a line. It's almost like you're drawing a line and then putting the dots on the line, right? So if data points end up lying exactly on a line, that will be very, very eerie, very miraculous, because in real life, the data points would hardly be so perfectly linear, even if we know by physics or by whatever real force governing the behaviors of the two measurements, physics will be one such area, right? Then even so, right, due to measurement errors, random noise, whatever, the data points will not exactly lie on the line. At most, they are hugging the line very, very closely. Then it'll be super, super negative, very far away from zero. And of course, in the middle, it'll be very near to zero, right? A value that is not very convinced about the shape of the data points being a line, right? Because the magnitude of the covariance value is very small. It's very small, near to zero. Okay, like this. All right. So this would mean that the line, very much a line with positive gradient, right? This would be a line with negative gradient, but we don't know what's the gradient, right? The gradient is another calculation. And this is no line. No line perceivable by the covariance. As if covariance can see, isn't it? Yeah. So because of its and yet covariance is just a formula, right? So it's quite amazing that just number crunch through this covariance formula, we get a single real number. And that number is telling us quite a lot of things, right? So that's the covariance. And I like to, of course, also uh, put down some behavioral issues of covariance, which is that first of all, um, the covariance of xy. Let me move this up. So covariance of x comma y is equal to covariance of y comma x. So that's called commutativity. Commutativity. Right? So they commute, right? They commute. Commute means they can swap places, just like 3 times 4 is 4 times 3. Next, I have to mention this. What happens if I put y to be x? That means I ask this number cruncher that y I can forcefully replace it with x, right? We seldom do that, but then in mathematics you can do anything because you're not touching reality. So x comma x, what happens? 1 over n xi minus mu x times xi minus mu x, which means xi minus mu x squared. And similarly for the sample version, same thing. That means we are calculating the variance of x for sample and for population. And by the way, I didn't mention whether this is for population or variance or for sample, which means it applies to both. Same thing here, right? So whenever I don't mention them, whenever I don't make a distinction, that behavior applies to both population and sample. And we like that, isn't it? Yeah, we like the sample covariance to be an estimator of the population covariance. So let me write that down first. Is the variance of x. Okay. Then we say covariance sample. Now I make a difference. Is an unbiased estimator of population covariance. So, which is nice, right? Because sample variance is an unbiased estimator of population variance. S square is an unbiased estimator of sigma square. Sometimes we cannot show the unbiasedness, so no choice. We will have to live with a slightly biased estimator. But thankfully, covariance is not, because we have to also ensure that it carries nicely over to the variance properties. Okay, so in other words, this means that the expected value of the covariance sample covariance operator is the same as population covariance. Okay, in that sense. Next, what else do we have? we can then say that covariance of a number, any number, I put a 7 here just for simplicity, but it can be any constant, is the same as covariance of x comma 7 using the commutative property is equal to 0. And notice this, right? So in other words, basically, we know from statistics and probability that constant population, that means a population measurement of 7, until infinity, yeah? The average is 7, the standard deviation is 0, variance is 0, etc. We know everything very well, right? This population set is going to be independent from any other measured variable. Why? What if I keep measuring other variables and they're also 7, 7.5, 7.2, 7? Doesn't matter. Because the population of 7 is never going to change. I don't care, right? Whether you tell me you just measure a height of 1.5, 1.7, 1.77, right? The population of 7 just doesn't care. Now, of course, this population of infinite number of 7s doesn't exist in real life, but in mathematics, we can do everything. Now you see the joy of mathematicians, right? They kind of like don't care. I can dream in my world, right? They can conjure up like mathematicians any number. Not they are mathematicians. They can conjure up like magicians any settings, any creatures, any entity they like. So this example, right? This example story should hopefully convince you that the population of 7 is independent from any other real life measured population, right? So because of that, we get a 0. Okay, so we can generalize that thought, and that is to say that if x and y are independent. Okay, I hope you still remember this notion of independence. We spent quite a bit of time discussing the hypothesis test for independence, right? The chi-square independence test. And we also talked about independence in how to determine, how to get the equations when we know that x and y are independent. So here again, if x, y, because we cannot reverse proof that xy is independent now for the next hour, for the next day, forever, right? We cannot prove that xy are independent, but we can theoretically go forward. That is, if we assume or if we are told that xy are independent. In real life, it will be if xy are having air gap, they are disconnected, they don't have information, no communication with each other, no information exchange with each other, then yeah, they are independent because whatever X does, Y doesn't know, doesn't care, right? Y will just go about its ways. Whatever Y does, X also doesn't know, doesn't get influenced, doesn't change its mind. It will just do whatever its ways. It's like two stock investors not talking to each other. So they just invest and one will win, one will lose, or both win, both lose. Doesn't matter. They are independent. It's like fairer, right? And if they start communicating, and if A is a dominant speaker, A may convince B, hey, you know what, invest in this stock, and then both will invest, both will lose, both will win together, right? Doesn't matter win or loss, but the thing is they no longer become independent. But sometimes we want independence in real life. In other words, we want to show or illustrate that they're not talking, they're not communicating, there's no information sharing, right? The antitrust kind of anti-competition kind of authorities will want to maintain that to ensure that vendor suppliers are doing on their own accord. They are not colluding right now. Yeah. So this has a very also serious consequence, right? If it is shown otherwise. But let me finish the sentence here. If x and y are known to be independent, then we can conclude that covariance of xy is 0. Okay. Now, a little bit of going backwards here is that if covariance, right, xy is 0, because we can calculate from samples and then say, how come, this calculation resulted in a 0.5 covariance, which is like very, very close to 0, right? Or 0. then what can we deduce? Okay, so in practice, okay, because theoretically I will answer, you can only say that they are uncorrelated. That means you are using a statistical term to say I just found that the covariance is zero, correlation is zero. Correlation I'll talk about. Well, but you're just saying what you have calculated. That's all. You're unable to say something more useful, more meaningful, more strongly in real life, which is to say, oh, I know that X, Y, they are not communicating. You cannot say that, right? Yeah, you cannot say that. So that's why in theory, we just say X, Y, they are uncorrelated. But in practice, this does give a very strong indication that very likely the data points are very diffused. They are not only non-linear, not only not looking like a line, but they don't look like anything. Okay, they don't look like anything. But there are some patterns that can upset covariance. That means they can trick covariance into thinking that the calculation will lead to zero. And I mentioned patterns, right? That means some symmetrical patterns you can see from here already in the formula, right? So if x and y they are in such a way that the negative signs cancel. Remember, there's no squaring, so covariance can go into negative values, and each term can go into negative values. So if the negative values, you put your dots because you are now controlling the sample's values, right? That you engineer it such that the dots give rise to negative values and positive values, such that when you add them up, they become zero, right? Or become 0.0001. Then you are essentially doing two things. Number one, you are tricking the covariance to be zero. Number two, you are the invisible force that arrange the dots to make covariance give zero, yet you have actively arranged the dots, which means the dots are not moving by themselves, right? X and Y, they are not on their own accord, thinking on their own. They are controlled by some invisible force. Number three, likely the pattern you end up with will be some sort of a symmetrical pattern, like parallel lines, parallel horizontal lines, parallel slanted lines, or whatnot. They are all kind of a symmetrical looking so that they cancel out. So that kind of pattern is not very difficult to create or engineer, and that's why you see that when you end up having a sample covariance of being equal to zero, we strictly speaking cannot immediately conclude they are independent. Now, having said that, for the parallel lines or symmetrical lines or symmetrical looking round circle or whatnot to occur naturally in real life measured values is also very strange, right? Very unlikely. That's why, in practice, when we get this, we may say that they are not independent. Not only that, we may also additionally say that the data points are diffused. Okay, that's why I took a bit of sentences to clarify that this is not immediate and only situation pointed at when you see covariance of xy being zero. Right? It could be some sort of very regular symmetrical pattern. Regular symmetrical pattern, they are not natural. Right? They are not natural, right? So they have to be forcefully arranged by some invisible force. And so that's why XY they are not independent. So how can you say they are independent when you get this, right? They are not independent. Okay. All right. So that's the covariance part. Now, so far so good and very nice, right? So covariance tells us some lines, no line, right? Problem is we're not happy enough. Okay. Now, I didn't put down the scale here. The X bar, what are the values? This could be 1 to 10. This could be 1 million to 2 million. This could be 1 gigabyte to 1,000 or 1 terabyte. Right? So the scale can be such a big difference, and this could be 1 nanometer to 15 nanometer, right? So the scale can be so large, when it is based on nanometer, your covariance, even if it's so large, that means it wants to indicate that in your chip design, because it's nanometer, in your atomic orientation, uh, there is a strong linear occurrence of the atoms laid out. Maybe because it's a piece of wire. And the so-called very strong will be exhibited as 0.0000, right? Because it'll be nanometer. So it'll be like 152 nanometer uh, squared. So very, very small value. Yet it is very strong relative to the X units and Y units, isn't it? So we have a problem. There's no absolute number to determine the strength, except when it's positive, we know that it is bottom left to top right. When it's negative, we know it's top left to bottom right. So there is a little bit room for improvement. This is where we can then introduce our good friend and another good tool called correlation. So correlation works based on covariance. I'm just trying to move myself to the right, to my left, and then I have some spacing. All right. So correlation works based on covariance, and we already have a good tool, right? Covariance, except for its range unpredictability. We can have a feel of it by looking at the range of x and y, but when I say unpredictability, it's more like when I just give you a number, like, oh, I know covariance of height and weight is 25.6. How do you process that 25.6? Is that large or small? So we know it's positive, but just difficult to ascertain what is the meaning of large, right? Given that x and y can have such largely varying scale. So comes correlation. So I'm going to use correl, right? Correl of x and y. And that's the population version. And thankfully, now we have a more generally acceptable symbol for population correlation, the Greek letter rho. All right, so that's widely acceptable and used in various textbooks and references, articles. So that's fine, and we can use that. So I will use it interchangeably because I want to also maintain the sense of symmetry in some sense, right? Connectedness with covariance, which is COV. Okay, so this is defined in terms of the covariance, population covariance of x and y, right, over the square root of variance of x and variance of y. Population, of course, right? So, okay. And what we have is therefore a adjusted or scaled down covariance. So if x and y, their values are large, right? Then their units will cancel out because if there are million dollars and $1 million, then the square root of variance of x, y will also be $1 million. Numerator, denominator units will cancel out. If it is micrometer, then same thing, it will cancel out. So that correlation is just a number without unit. Okay. So at the same time, we also have corral for sample, put a tilde on top. And we also have a very generally acceptable letter R. That's for correlation, not C, but rather R. And that is, of course, defined similarly with the covariance of sample covariance of xy over the variance of x and variance of y. But square root of variance of x, sample variance of x, right, will be just s square x in that sense. Not the capital S, not the capital S that I defined earlier on. This one, this is SSX. It's just the sample variance, but without dividing by n minus 1. Same thing here. This is the sample variance for y without dividing by n minus 1. So as you can see now, we want to talk about the square root of the sample variance for x, right? So we can directly take the square root of the s x square. That's the sample variance for x, right? But square and then square root, it becomes just sx times sy, which means the sample standard deviation for x times sample standard deviation for y. Now, the sample version of covariance is something I like to provide a more rudimentary level of expressing the formula, which is that means at the more basic level. So now we're going to look at this covariance. Covariance, sample covariance, just a quick reminder, right? Just a quick reminder. Sample covariance has a denominator n minus 1. So is the sample standard deviation. It will have a denominator of square root of n minus 1. So is for sy, which has a standard deviation, which has a sample standard deviation denominator of same thing, square root n minus 1. So together, they become n minus 1, right? And covariance in the numerator has a denominator of n minus 1. So the denominator here and the denominator here, they cancel out, right? So we end up getting summation of I from 1 to n, xi minus x bar, right? yi minus y bar. This divided by the square root, right, of summation from I equals to 1 to n, xi minus x bar squared times summation equals to 1 to n, yi minus y bar squared. Right? So in short, this horror formula is basically just, thankfully, we can just write ssxy over square root of ssxx. All right, just ssx and ssy. Let's just be clear here because this is a very core definition of our calculation. Okay, so we get s as x and s as y. Okay, that's why you see it's quite helpful to have a useful, appropriate short form for all these summation values, which are just sum of squared deviations, right? So that's it. And this is useful for calculation. We can just number crunch this to get our R. Okay. Now, R is a sample correlation. Rho is actually what we are after, right? Because population correlation is what we are after. It is the entire population of the dots, not only those that we have observed, but the hidden ones behind, right? The many, many, maybe millions of other dots, the millions of other people's height and weight that we haven't seen or measured. We wonder whether those form, a line. That's more important, right? Yeah. So it's not just our sample forming a line. But of course, you can also imagine that without the population forming a line, why would our sample form a line? But maybe due to low sample size, we haven't touched reality often enough, right? Many times enough to get a feel of the entire shape. So the four blind men and the elephant comes in very aptly here because we haven't touched the shape, so we don't know the shape of this elephant, right? You're just touching one time, you can't tell. So it could be that because of low sample size count, we only manage to get a few points here and there, and we don't know. And then we conclude it's not a line, but actually it's just not enough points to form the line. Right? So it could be one or the other way, and we don't want to conclude wrongly. So we need to have higher sample size. Okay, but that's the definition for correlation. What good has it got, right? Well, we certainly will have to have this plus the strength being adjusted, right? Because that's exactly the weakness of covariance. It can tell us the lineness, whether the points fall on line or not, but we just don't know the strength, how large is large, how small is small. That's why we end up trying to have this device, correlation device, right? So let's put down some charts, perhaps. And I'm not going to draw big charts, right? So just a few of these. 1, 2, 3, 4, roughly like that. Okay. So the idea is that for correlation, whether it's rho or r, okay, the correlation will go from -1 to +1, and it will sit at 0 if the data is nebulous. So -1 would mean this kind of line, this kind of data points. Let me put them here. Okay, that is perfectly hugging the line, right? And it doesn't mean have to be diagonal, touching the corner to corner. It can also be like this. So it will be like this, perfectly hugging the line, right? Perfectly hugging the line. And 0 if the data is diffused, just like the covariance case. Can't tell, right? There's no pattern and no line. No pattern and no line, they don't mean the same. So I'm saying something very too strong. What correlation says is no line. So therefore, this shows no line. That's correct, right? And of course, anything else in between would give rise to the numbers in between. Some kind of a fat line. The data points show some sort of a fat line. The fatness is because the data points start to disagree with each other, right? Now. So whereas some points will show a line, others try to curve or bend or fall apart, go into the outliers, right? That we no longer can very reliably, say that it is aligned, but it is also not completely not aligned. That kind of meaning. So that's why it's good that we now not just have a LED light that lights up or shuts down because I see a line. I don't see a line. The kind of binary information, which is good, but can we have better, right? Can we have shades of gray, not just black and white? So just for illustration, another line that is like this, also having a negative gradient, but a different gradient from the first, right now, is going to show up as -1 with correlation, because correlation is not showing the gradient. That's the distinction. So you get +1 whether you have the positive, whether you have a very large gradient or a shallow gradient. A shallow gradient means the line is very close to horizontal, right? And correlation is saying, well, no. It's correlation indicates the huggedness of the data points. How strong the data points are hugging to the line. They're not deviating much from the line, right? So that's the correlation information. And likewise here, right, just show a little bit more diffuse points, but not exactly not aligned. So now we can see some sort of a curvature there, right? Can you say this curve within the context of this square? Can you say it is a line? There can be a line, right or not? Yeah, because you cannot say it's not a line. Can you say there's no pattern, like zero case? Can't say. Can't tell. So same thing here. I can show another rather hugged line. Hugged line. The data points are hugging a kind of line, but it's not a line. It's a curve. It's a curve, right? So that if you do sketch a line, no good line can be found. And yet you can't say it's not exactly a line because there seems to be a line. So that kind of information and its bending kind of like in the positive gradient sense will give rise to number in between. What can give you 0? Well, it could be this. Some sort of perfect harmony. Yeah, very, very symmetric, no matter how you look at it. Very, very symmetric. Yeah, okay. So that would be, in fact, it should be more. That would be the kind of situation where we are able to visually see that there is some regularity, right? In fact, we'll just say it's a circle. And for x and y, example, height and weight, for x and y to line up so nicely in a circle, you should be very amazed, right now. Yeah, but we will be very amazed. How would that be, right now? Yeah, because it's supposed to be natural occurring. So if that circle appears, what happens to correlation? If you calculate it, you get 0. So then it says, oh yeah, it gives rise to this kind of pattern. No, not really, not really, right? So there is some sort of relationship. So correlation actually is not a good term. It should be collinearity or something like that. But no, that's another notion. It should be yeah, but correlation detects line, right? So keep that in mind. Correlation, very strong line means hugging the line. The data hug the line, doesn't give you the gradient. 0 means no line. So is it true that we say there's no line? True. Okay, so for the circle pattern, we can say there's no line because no good line fits any given point to represent all the points. No good line. There's not a good line to represent all the points. Right. So we can say there's no line. But no line doesn't mean no pattern. So this is important, right? So when we get from number back to pattern, we need to be very careful, right? 0 implies no line. And it could be no pattern at all, some pattern, some symmetry, right? And so on and so forth. But just remember, don't over conclude. All right. Okay, so that's the point to make here for correlation. Okay. Next is when we perform all these calculations, right? I just want to also highlight another maybe illustration just to show how our x and y, their values on the grid, yeah, is they are being processed. So we have a x here and we have a y here, right? Of course, you can call it height versus weight, no problem. Just to give it a bit of a context, right? So suppose we have 5 friends. Miserable. Okay, so we have 5 friends. We ask them, all right, 5 friends who are willing to let you measure their height, right, and their weight. Okay, so you have 5 friends. You measure their height, their weight. This is point 1, point 2. Then we have point 3, point 4, and point 5. Okay, so let's say we manage to get this. So it's supposed to be like this, although, you know, it may be that you have skinny friend, obese friend, whatever, right? So somehow there will be. So 5 is not a lot, but I'm just trying to illustrate. So I'm not going to like spend half an hour trying to put the dots right. But what am I trying to show here is more about the computation. So when we perform the numerator in particular, right, the numerator, so which is actually the covariance, right? When we perform covariance, what is the calculation involved that give rise to this magical property, right? Of wow, positive value is positive line, negative value is negative line, and what is going on there, right? So so let me just quickly, because sometimes I plot and I narrate at the same time, then I say the wrong thing or I draw the wrong thing. So here I want to give the center of gravity, correct? Yeah. So of course, all these computations, because they are done legacy wise, it's always using the mean and the standard deviation, right? So it's not median, never median, um, never quartile. Okay, so x bar and y bar, yeah, it's because they are the center of gravity. So this may be 0 on the bottom left, but this can be 1 million units away, 0.1 unit away, right? Because these are all small measurements or whatever it is, right? So the center of gravity will always be the center of gravity, regardless of the units of x and y. Now, what happens? Okay, so we have the center of gravity, and the idea is that when we perform yi minus y bar, yi minus y bar, what is happening? So yi minus y bar will be this one, right? Because it is y1 minus y bar. And the x1 minus x bar will be this distance, so that we can write it down as this is y1, maybe a bit tiny, but you can basically see for yourself. And there's no absolute value, just sign included, right? Sign included. y1 minus y bar, and this part will be x1 minus x bar. All right. Yeah. And of course, I'll continue this onto the next point, right? Y2 minus y bar, and so on. But I'm not going to squeeze in that. You understand that? And over here we have the y3 and then the y4, x4, right? And then the y5, y5. This is x5. This is y5. Okay, so let me also annotate a few more, perhaps the visible ones, right? So this one is y4 minus y bar. This one is while x4 minus x bar. This is, okay, this part is visible. x5 minus x bar. This is y5 minus y bar. Okay, you can, you can appreciate, right, that these are just rectangles, right, rectangles. Okay, so I didn't shade the other two. Did I miss any? One, two. Okay. Okay, good. So what is going on is that when you calculate the product, when you multiply them, what happens? You're getting essentially the rectangular area, right? Yeah, you're just finding the rectangular area. But more importantly, notice that this here, y1 is below y bar, right? So y1 minus y bar is negative. x1 minus x bar. x1 here is below x bar, below the value of x bar. So x1 minus x bar is also negative. Negative times negative, you have a positive area. So interestingly, we have a positive area here. Okay, we have a positive area here. Can I understand that? Because we have a negative y and a negative y distance and negative x distance. So all the rectangles in this quadrant to the lower left of x bar, comma y bar will have positive area. What about this side? Clearly, it will be always positive x delta times positive y delta away from x bar, y bar, right? So I hope it's not difficult to convince you here that the top right quadrant will also have positive rectangular areas. All right, so there are positive areas as well. Okay, so that's why it's not easy to see that the other two quadrants, what do you expect? Either both are positive, but cannot be, right? Because here the x distance is positive, y distance is negative, right? And we allow for negative values, negative products to go into the summation. So we have a negative area here, and the first quadrant, of course, better have some symmetry. So we have negative areas here. Now you understand that whenever the dots happen in the first, this is the, where's the first? This is the first quadrant, first, second, third, fourth, right? The first and the third quadrant, the areas, the data points that are happening there, they will be reinforcing the positive area, right? They keep adding to the positive, contributing positively to the total sum. Any data points that fall into the second and fourth quadrants, they deduct from the accumulated positive areas. So if you have a lot of data points in the second and fourth quadrants, they will keep subtracting that, so much so that if they balance out the positive area, you are going to end up with very little area, like near to zero or absolute value. So it can be negative 0.1 or positive 0.05. Right? So very, very little area in the absolute sense of the covariance. So the other way around is that when the data congregates around first and third quadrants, and very little data, like our case here, right, contribute to the negative area, then you keep having positive and your covariance will be very positive, very large. And if covariance is very positive, very large, it will make correlation very positive and very close to 1. Very close to 1. Right? So that's the reason why, because the sign is entirely driven by the covariance, because denominator is always positive. So the sign will be driven by the covariance. And the covariance has positive when data is stronger, like more points, more dots, more positive areas in the first and third quadrant. And covariance will be negative if it is the other way around, second to fourth, very, very populous, right? A lot of points there. First and third, very little, very sparse. Okay. What about the case when all the points are in the first quadrant and the fourth quadrant? Not possible, correct or not? Not possible because our x bar, y bar is always going to find the new center so that some points will be on the left, some points will be on the right. It cannot be all points congregate on first to fourth, first and fourth, or second and third quadrants only. Not possible. Or the other way around. First and second quadrant only, third and fourth quadrant only. Cannot be. Because x bar, y bar will find the new center. There will be some points everywhere. Right? But we allow, or rather x bar, y bar will still be very balanced if points are mainly in first and third, or points are mainly in second and fourth. Other combinations, not possible. That's the whole magic, right? That makes covariance like able to see a line when actually it is more like partitioning the screen. Your screen has 2000 pixels by 1000 pixels, right? But when your eyes look at it, is there a line or not, right? You're just going to very broadly divide it into four quadrants and then see if this big cell and this big cell, they are colored, yes, right? They are lighted up, yes, then there's a line, positive gradient, right? But I would be very fuzzy about the whether it's 45 degrees, 30 degrees, or what. And same thing here, if the second and fourth quadrant, they are populous, they are very densely populated by the data, then yes, I see a line, right? Like this is being lit up, and so you have the negative gradient line. It's both simple and yet very magical to be able to see that, right? So just to illustrate, I mean nothing new here, but I hope you can then appreciate that little bit magic there when we just allow for the areas to be negative, right? And a lot of times you square it to get rid of negative sign. A lot of times we take absolute value to get rid of the so-called meaningless negative area. But covariance exactly takes advantage of this to give you this artificial intelligence, right? If you say recognizing a line is intelligent, then yeah, this is artificially computed intelligence. So just something cute, I think, to share with you on this. Now, I also like to give you a list of the properties of correlation. So first thing first is that the correlation, and I want to write just correl so that it again also means population correlation and sample correlation if I don't make the distinction. So the correlation of x and y is the same as correlation of y and x, right? In other words, the line that we see, basically, if it's a line, is a line. Doesn't matter how you reflect it or whatnot. Doesn't matter, right? It's still a line. Next, we want to talk about the correlation of x and x. What happens? Am I correlating with myself? Of course, right? And it is always a +1. Better not be -1. Huh? Like you go west, your shadow goes east. That would be something weird. Okay, so I am always correlated with myself. Although that is a bit trivial and kind of a nonsense, it is true that a variable is always strongly the strongest positive correlation with itself. Okay. And next thing is of course same thing due to covariance, right? Correlation of a constant with any measurement is 0. There is no correlation with the constant population of 7 or 11 or 15 or 1000, doesn't matter. Okay, so that's the property there. Next, we want to talk about the correlation of AX and BY, right? So this has got to do with the covariance property, which I realize I haven't added in, so I should add in that the covariance of AX and BY, right, is equal to the AB, A times B, of the covariance of X and Y. So it's like we extract out the constants, which is nice because any multiple of X and any multiple of Y, does it change the covariance? Does it change the shape? Answer is no. All right, so it's as much a line as is the original X and Y. So if X and Y already is a line, then AX times BY, that means I stretch, right? Or I compress. So 2 times of X means I stretch the x-axis. I rubber band it, I stretch it. Or I halve it, 0.5 times Y. So I compress the y-axis. I'm basically, stretching and compressing the line, right? So a line, is this still a line? Sure. The gradient will be affected, but is the shape still a line? Answer is yes. So if you start with a line in the first place, then you stretch it and compress it no matter what, end up you only bring out the values. That means the covariance value will be enlarged or diminished, but the line is still a line. The covariance value is the same. What about correlation? Okay, correlation, because we are going to nullify the scale of the covariance, right? We are going to kind of make sure it doesn't, correlation always stays within -1 to 1. So we will end up getting, if you kind of play around with the derivation, we get the sine of AB. Because the sine is important, the sine of AB will be maintained. Right? So the sine of, not A comma B, sorry, A times B. Yeah? Make sure it's clear here. Okay, so the sine of AB is a function that is +1 if AB, the product, is greater than 0. And it is -1 if AB is less. And it is 0 if AB is 0. Right. Fine. So, yeah, so we have correl xy. So in other words, if the correlation is already +1 or very near to 1, then the shape is like a line, right now. Yeah, it's very, very hugging the line, almost like a line. And you go and scale it, stretch, rubber band, stretch it. Or you compress it by multiplying by a small number. Doesn't matter. You can multiply all you want, but the AB will vanish. Only the sign remains because look, I can multiply by -1. So my y-axis will be flipped downwards, right? So a positive gradient becomes a negative gradient. Then my correlation should flip from +1 to -1. So it's very clever here to just multiply by the sign of the product of AB. So A can be negative, B can be negative, minus times minus becomes plus, so there's no change in sign again, right now, yeah? So that's the final form of the correlation. Okay, and we also have the independence kind of ruling. If x, y are independent, all right, what can we say about the correlation? What do you think? Well, correlation for both, right, population and sample, due to the covariance of population and sample being 0 whenever x, y are independent, we will get 0. That's right. It's quite obvious here, yeah, because variance of x, y, they can never be 0, right? Not in practice. Right? So Sx, Sy will never be 0. So the only time correlation can be 0 is because covariance is 0. Okay. Now what happens is that statement of what I mentioned just now for covariance, but I think it's more easily said in the case of correlation. So if correlation of x and y is 0, right, then it doesn't imply that x and y are independent. We will have to go through the chi-square independence test, right, to do that. So, and that is only also proving that, or showing that x and y are statistically independent, right? Any statistical test or formula or theory can only go so far as to say, well, you fit our definition of what statisticians call independence, right? But can numbers inverse prove that the two objects in real life are air gapped, right? They are not communicating. Not possible, right? At least not that I know of. Not for now. Okay, so that is the property as a list, as a convenient list. And just one more, small little formula for your notes that I find very useful. So I want to share that with you, which is that we keep talking about gradient. Covariance is not gradient. Correlation is not gradient, right? Gradient is another formula. So what is gradient? Huh? What happens if we have a line, right? So very briefly, very quickly, the line, right? The line, we can write it out as expressed by a equation, right? So a line can be expressed as an equation. So when we do find a line of data points, considering only two-dimensional space, huh? So x comma y, weight comma height, right? A line of data points can be described by a line equation model. We call it a model. We don't call it equation, because we are trying to describe the connection between y and x, right? An equation means we will solve it, which is not really the meaning nor the intention intended here. So the model is going to look like y equals to v0 plus v1x. We typically say y hat because we can artificially plug in any x, right? And then we get some y values that have never been observed before, right? So we observe 5 points, for example, here, right? So we have 5 x values, 5 y values, but we can also insert x equals to this value. Like if this is 1, 2, 3, 4, 5, we insert 2.2. So we never measure the point 2.2 and never measure the y value at 2.2, but yet we can calculate it. That calculated value is called the y hat value. Okay, so I think it is helpful to quickly have that chart here being drawn. Okay, so we have the y and the x bar and the y bar. Right, so we have very quickly the dots like that. No need to be to scale, but ensure that x bar and y bar, they are at the center of gravity. Okay, good. So now that we have this, we can now, because I don't want to make my diagram too intense in the previous one. So I'm just going to quickly replicate that. Okay, so now I can have a line, right? So let me use this orange color. I now can have a line. This is the line that best fits the given data. So we call this the least square fit. The sense of best fit, best fitting line. In the sense of least square. Least square errors. What's the least square error? Least square error is number one. This is the error. This one. Right? This difference is the error. The square of the error is going to be inducing these tiny little areas again. Yeah. So if I may just draw here, all right. So you can imagine, right? So a square, right? Because square in algebra means literally the square box geometrically, right? So we can see the square area. So when you add up these square areas, it will be the least you can find. Then if you tilt this line, jiggle it around, right? Of course, very nonsensical gradients, you can forget about it. But we're talking about disagreements here, right? Because some of you may say, why this line? Why this gradient? I like this better. I like first and last point connected. The rest are just hugging around, just floating around the line. Some of you might say, no, 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 I want this one because then 3 points will be closest. These two, forget about them, right? But not all are wrong, right? Why should we agree on one particular line? And we agree on this particular line because its property is such that if you calculate the errors square, right, and you add them up, because all the points will contribute to error, so you cannot favor first and last, right? So if you add them all up, the total error squared will be the least amongst all other lines total error squared. That's nice, isn't it? Yeah, we can have that property. So this is called finding this line means B0 and B1 is the role of linear regression in the simple sense, because we have one explanatory variable x. Simple linear regression. Okay, so and what I'm after is, of course, to give you formulas to compute for B0 and B1. So B1 first. B1 is going to be the gradient and is given by SSXY. It's a bit like y over x, except in statistics, here we need the xy, SSXY. So SS of x. And B0 is simply y bar minus whatever we have computed in B1 times x bar. That's all. Finish. Very, very simple. Okay, as the last segment of this discussion, I just want to quickly give a numerical example similar to this graph on top. The numbers will be, of course, randomly picked, but the idea is they mimic the relative positions. So I have very quickly 5, 4, 6, 7.5, and 8. And y would be 8, 6, 13, 7, and 11. Right. So assuming those are the measured values in some appropriate units, notice they are all paired. Huh? Yeah, it's like height and weight. Always remember this example because it's very personal, right? You always know you have height and weight. And we always have an intuitive notion that height and weight, they are somewhat related, but not fixed, not hard fixed, right? Because we have tall people weighing light, we have short people weighing heavy. So, and yet there's some sort of a progression. That means the taller you are, you should be heavier, right? Among say all the skinny people or something. So yeah, so this is an excellent example, and what we want to do is to, of course, calculate. Right? So first we will, of course, note that the x bar, y bar is going to be 6.1. That's our x bar. And 9, that's our y bar. And sx, our sample standard deviation, 1.673. And our y sample standard deviation, 2.915 as y. And then we want to calculate a bunch of values, which is x minus the x bar. X means the xi's, right? Then y minus the y bars. And then we have the product, x minus x bar times y minus y. Yeah. Okay, so what happens next is I want to make sure the numbers are clearly separated. Okay. So this minus this, we get negative 1.1. Okay. Then negative 2.1, negative 0.1, 1.4, and lastly 1.9. And the other one I will just quickly write down because it's a very nice integer. So minus 1, minus 3, 4, minus 2, and 2, respectively. Okay. And then what happens is we multiply them together to get the product, right? So remember covariance? Covariance is the sum of the products. Then you divide by n minus 1 if you are calculating sample covariance, and we'll do that, right? So multiply them, we get 1.1, 6.3, negative 0.4, negative 2.8, and finally 3.8. So, of course, we will sum them up. And this part is very important. So, we'll sum up the vertical square sums. Okay, if we square them and sum, right, so we sum the squares, we will get 11.2. If we sum the y minus y bar squared, that means this becomes 1, 9, 16, 4, 4. We'll get 34. This we don't square because it's already producted together. So we just directly sum. So we get 8. Okay, so this becomes our SSX. This is our SSY. Remember to square it, because for ease of writing, clarity here, I just didn't square. But when I add up, I better square first. That's why it's positive, right? But this one we don't. So you see there's a little bit of a different treatment here because this already have the products together, x and y. So you cannot square and then square, and then you have square of too many squares, right? So cannot. So and this is our SSXY. Okay. Now we are ready to calculate, right? And the idea is that our n minus 1, what's our n? Our n is a our n is 5, right? So there's 5. And our n minus 1 is 4. Okay, good. Then what happens? Well, our covariance, first of all, sample, right, is going to be equal to SSXY over n minus 1. Right? So there'll be 8 over 4. You should get a 2. Perfect number. And use your Excel covariance.s to find that out. Right? Then we have our correlation. Our correlation is correlation. So correl of xy is going to be covariance 2 over, or rather, square root. I'm going to just try out this formula here, right? So square root of, so SSXY, so that'll be 8. That'll be 8. Divide by the square root of SSX times SSY. So that's 11.2 times 34. Right? So what do we get? We better get 0.40996. We have to keep the 6, otherwise I have to change to 0.41. Very, very close to 0.41. So that's our sample correlation. Right. So that's our, should we say, is looking positive, right? Yeah. So it's looking like a positive gradient line. Right? And we can, of course, calculate the gradient. The gradient is going to be B1 equals to SSXY. I'm just entirely using the SSXY, SSX, SSY values, right? Over SSX. So that's going to be 2 over 11.2. So we get 0.7143. So indeed, quite a line that is near to the gradient equals to 1, the 45-degree line, but lesser than 1, right? So it's slanted down, dropping down. That means the angle is less than 45 degrees. So that makes sense. And just we're almost done, right? Because we have x bar and y bar, so we can calculate b0 being y bar minus the b1 that we calculated times our x bar. So we have our 9 minus 0.7143, sorry, times our 6.1. Ending up, we get 4.6429. So our simple linear regression model is y hat equals to B0 first, 6429 plus 0.7143x. That's right. We did it entirely just using manual calculation. I did use calculator in Excel, to be honest, but it is so considering the the outcome that we can get, the very rich model that we can get. We only just have to use a bit of a simple calculation aided by calculator just to make the calculation faster. That's all, right? And then we are done with the model. Of course, for multiple linear regression, that means when the right side has not just one x, but there's x1, x2, x3, x4, x5. Then number one, the model will be more, I should just say richer, right? Having more content, more data, more values. Number two is likely more useful. Number three is also very for sure, is that it will be expensive, right? A lot of hard work, a lot of measurements, a lot of sampling would have to be done. And number four, the mathematics involved will be also a lot more complex, although the thinking is entirely the same. All right. In multiple linear regression, in other words, we have more access to explain the why, to predict the why. We have more consultants, right? If one axis, one variable is a consultant, is a measurement, is an input, then we have more consultants, more inputs, discuss, right? To finally give one number, which is to predict the why. And so, if you imagine that a team of not just two, not just three, but five doctors discussing whether a patient should undergo the surgery and how to conduct the surgery, then that outcome is the why that we are predicting. And the team of five doctors, they are the five axis or variables, x1, x2, x3, x4, x5. Of course, the whole calculation will be much more intense. Definitely, there's a lot of work to be done, but the line of thought is still the same. In higher dimensions, the line is no longer a line, but a sort of a hyperplane, right? Sort of a line existing in a high dimensional space, hyperplane, and we'll need various values to come up with a single value of the y value, right? So, how to get the model done? It will be just B0, B1, B2, B3, B4. Once you can find those B coefficients, the several coefficients, using the data that we obtained, then we are done. We know the model and we can start predicting using the model, right? So, but for this video, we'll end right here with this numerical example to remove the fear that it is a very complicated calculation because we did it almost entirely, can be done by hand, right? But just to make sure I'm not making silly mistakes, I did use a bit of help from Excel and R, but essentially this is very doable with few pieces of data. But this simplicity in line of thought in the calculation procedures carries through into many more samples, hundreds and thousands of more samples, and breadth-wise, many more x variables, explanatory variables, x1, x2, x3, x10, x20, right? So you are in the 20-dimensional space plus one, right? 22-dimensional space, still okay, no problem. Okay. So I'll see you then in the subsequent videos to discuss about multiple linear regression. Thank you for your attention.